All right. Hi, everybody. My name's Sam. And this summer, I spent some time working on a project describing quantized vortex interaction in superfluid helium. So basically, we found formidable evidence that an intersection between quantized vortex lines results in a line separation distance, which fits the form of a power law. So I'll explain a little bit about what all this means. So what are quantized vortex lines? Essentially, if we take a bunch of helium and cool it down to its liquid state at around 4 degrees Kelvin, a component of this helium acts as a superfluid, which is a fluid with zero viscosity. In this fluid, there's turbulence, which causes the creation and flow of vortices, right? Basically, mini little tornadoes, and they have a quantized circulation, which is why they're dubbed quantized vortex lines. And occasionally, these lines will interact and cross each other's paths in what's called a reconnection event. So here's a little picture of them. During an event, the rate of separation distance between the two vortex lines per unit time is not constant. So essentially, they cross over each other, split, and then they kind of like jump away from each other. And then that distance becomes greater and greater and greater, but the rate at which it moves becomes slower and slower. So in order to see these vortex lines moving, we release a bunch of ice particles into the helium and then shine a laser onto it so that we can see these little pictures like this. And then we collect the data of the position of these particles in the lines to run some like dynamical analysis. So my job for the most part was to collect the data that we needed. So for the first few weeks of my summer, I was really just turning these images into actual quantified data. This, it'll allow for any more work from the future in my team to be able to actually do some real analysis. And from here, I had to write a code to connect all the points in these lines so that we could get a more accurate distance measurement. And then here I have graphs of all this data over time. So we have the normal plot of how the separation distance changes over time. We have that in log scale, so that the slope of this line should be the power at which that power law fit forms. And then this is the time versus the square of the distance. Our hypothesis was that that power in the power law was about 0.5. So we should see a linear relationship in this graph, which it seems to fit pretty well. So my next job was to run some statistical analysis on it. We performed a curve fit to this formula with fitting parameters A and alpha, where A is just a separation coefficient and alpha is the power law. We have some of the graphs down here. So it fits our form pretty well. And we did this for each event that I could find. I filtered through all these videos and found a bunch of these. And all of the values were very similar and they were very, very close to the value we expected. So our next step is to perform some real error analysis. There are a lot of sources of error in this type of photography that we used. And that will allow us to get a much more specific value and uncertainties. So basically, by processing data from these images, our team has confirmed the viability of describing reconnection separation behavior. And really, it's kind of showing that there's more investigation to be done. The whole point of this little project was so that now my team knows to take more data and to keep doing more advanced statistical analysis. So what's next? We also need to determine that coefficient out front. This coefficient actually changes. We have evidence that it depends on the angle at which the two vortex lines strike each other. We need to finish some error analysis, get more precise values, and then we're also going to analyze some trends of the lines before they reconnect. After that, we're going to do more events, more analysis, and we'll have some pretty exciting results soon. But yeah, that's all I have. Thanks so much to my team, Dr. Weglow and Dr. Yolanda Tang, and everybody else in the REU, especially my roommates. I really appreciate the support. Thanks very much.